Hello and Assalamu alaikum everyone. So in the previous sessions we have been discussing regarding the eigenvectors, and I told you that they are required for the understanding of SVD and PCA. And let me revise a bit so that we're on the same page and you understand the concepts better. So what about the eigenvectors? So if we have a matrix A, so if we have, let's suppose, a vector V, and then we call this vector as an eigenvector if this is equal to some lambda times V. That means if, let's suppose, we have some vector space and in which this A is a linear transformation. If, let's suppose, we have this vector V, if this A is applied onto this V, so what this A does is it will only scale this vector up. It will either expand it or it will just diminish it a bit. So that's the meaning of the eigenvectors that we saw in the previous class. Let me just remind you about the properties of eigenvectors. So in that we said if you have to compute this, so we basically represent it with A V minus, we'll just write A V minus lambda V is equal to 0, and then taking this V as common, then we wrote A minus lambda I is equal to 0. Then we saw there are three cases possible. So what are the cases possible? So either this V is 0, but in the definition we said V should not be equal to 0. That's a trivial case. So this should not be equal to 0. So then what is the other case? The other case is that if this matrix is basically invertible, that was also not a good case. So we said it should be a singular matrix. It should be a singular matrix. That means it should be non-invertible, this whole matrix, this one. So how to put that? That means determinant of A minus lambda I should be equal to 0. And then we saw some properties as well that I would like to mention. So properties. So what's the first property? We said that if we have A and we have its transpose matrix A transpose, we said that eigenvectors of both of these are same. Eigenvectors of this is equal to the eigenvectors of A transpose. Okay. Then we even say that in singular matrices, if we have matrix A, which is a singular matrix, let's suppose this is a singular matrix. That means it is invertible or non-invertible. Determinant is equal to 0. So for that we saw that it has at least one eigenvector which is 0. At least one eigenvector for this is 0. And we can also prove one property for the inverses. Let's suppose we know that this ax is equal to lambda x or av is equal to lambda v. So if we want to find what is the, let me just point these properties out. So this is the other property. We said that if we have this a lambda is equal to lambda x, so if we just apply the inverse on both sides, that will be a inverse of a is equal to this lambda a inverse of x. So that means if we just cancel these out, because this is equal to identity, so we need to find what is ax. So a inverse of x basically will be equal to 1 by lambda x. So here if you see that the eigenvectors remain same, but the eigenvalues got reciprocaled. So if we have a matrix A, for that if eigenvalues are lambda and eigenvectors are this x, so what I said is that for the inverse matrix of this A, for the inverse of this A inverse, so what we have is we'll have the reciprocal of the eigenvalues that we had for A, and the eigenvectors will remain similar. Is it clear? Then one more property that we I think mentioned is that if we have diagonal matrix or the triangular matrices. So if we have diagonal matrix or the triangular matrix, for those eigenvalues are equal for to diagonal elements. So eigenvalues are equal to diagonal elements. But for special two matrices, that is diagonal matrices and for diagonal matrices and triangular matrices. Okay, then we also defined something called as a trace of matrix. So for a matrix A, we define trace. So trace of A is defined is written like this. So it is basically equal to the sum of diagonal elements. So mathematically we can write it summation of A I, because the diagonal element basically has same. So we say that the trace of A or the summation of diagonal elements is equal to the sum of eigenvalues. Okay, so this is one thing. So then we said something about the determinant. We said determinant of A, determinant of the matrix, is equal to the product of eigenvalues, is equal to the product of eigenvalues. So this can be written mathematically like this pi, and then eigenvalues are lambda j. J goes from 1 to n. This is from j goes from 1 to n. In the similar way, we had this I goes from 1 to n, because we consider n cross n matrix, and we saw that in order to have these matrices, that they should be square matrix. So because we are finding these things for the square matrix in particular. So is there something else left? I think these are the properties that we covered. Maybe one more property I would like to mention somewhere is that. So eigenvectors and eigenvalues can be at most one, at most n. Sorry. So for a matrix, let's suppose if we have a matrix A which is n cross n. For that, what I said is, I said that the eigenvalues or the eigenvectors, I'll say eigenvectors, will be at most equal to n. This is written as less than equal to, basically means at most. Okay, so are there some properties that we left? I don't think. Okay, so these are the properties, and this is just a revision that we saw in the previous class, and we saw some matrices, and we also did some examples. So again, to reiterate, this A here is basically a linear transformation, or A is a matrix which describes a linear transformation. Linear transformation, what it does, it will just transform the space into somehow, and it will transform that vector space. So all the vectors, they will be transformed, but there will be some special vectors which won't be transformed. They will be lying in the direction they were initially, but they will be just either stretched, squished, or maybe at the same place. So we call these vectors as eigenvectors. So here these are called as eigenvectors. And the scaling factor by which they were scaled or squished, so we call it an eigenvalue. This is the eigenvalue. And then we said that in order to find that, and we need to put the determinant of a minus lambda I is equal to 0, and from that we'll get the lambdas, and corresponding to lambdas we'll get the corresponding to these eigenvalues we'll get the eigenvectors. Then we saw some properties. Again, to reiterate, the first property is that at most the number of eigenvectors will be less than or equal to n. That is, at most there will be n eigenvectors for a matrix which is n cross n. Then eigenvector of A is basically equal to A transpose. You can prove this property easily. And then if we have a singular matrix, that's in a matrix in which we have dependent columns, in which we do not have all the rows as all the columns as pivot columns, that is determinant for that matrix is 0. So for that, at least one eigenvalue will be equal to 0. Then I also said that if we have a matrix A, its inverse will have the eigenvalue as reciprocal of the eigenvalue of A. That's what I proved. And then these eigenvalues are equal to the diagonal elements of that for two matrices, that is for the diagonal matrices and the triangular matrix. If you are given a diagonal matrix, let's suppose like this. So 2, 2, 0, 0. If somebody tells you what is the eigenvalues for these matrices, so you can say that directly 2 and 2 are the two eigenvalues. Directly these are the eigenvalues. If somebody says you, for example, 3 and then 0, 4, 1, this is again a triangular matrix, so here the eigenvalues will be 3 and 1. Okay, and you can prove these properties though. Then we define something called the trace of matrix. So trace of matrix was the sum of diagonal elements. So if we have a matrix 1, 2, 3, 4, so trace here is 1 plus 4, so that's 5. So trace of matrix is 5. So I said the trace of any matrix A is equal to the sum of diagonal elements. That's also equal to the summation of the eigenvalues. And then one more property is that if we have the determinant, so determinant of A is basically equal to the product of eigenvalues. Are these things clear so far? Are they clear?
Yes, sir.
Yes, sir.
Okay, then we can move ahead with the subsequent topics. So today we are going to see an important topic of diagonalization. So let me just pause here for a second. I'll see if I have missed something which is of importance, so that I can also cover that. Just give me a moment. Now we'll see what is known as the process of diagonalization, and we'll call this as diagonalization. It's a really important topic. So we'll actually see different matrix factorization techniques. So these are called matrix factorizations. So what is the meaning of composition? So if you have, for example, a matrix A and B, and if we multiply them together, we get a matrix C. We call it composition of the two matrices. So we'll multiply A with the B to get C. So in the similar fashion, if you have been given matrix C, so you can decompose it. So you can decompose it into A into B. These are called matrix decomposition or matrix factorization. So we call it matrix factorization, matrix factorization, or matrix decomposition. These are really important topics. The SVD, everything, those problem basically they are. If you see this SVD, it's basically a matrix factorization. It's basically a matrix decomposition. So I hope that decomposition and factorization is clear. So let me tell you why are these important. So if you see the modern recommending system, let me tell you an interesting story first. So that I motivate these examples where are they used. This diagonalization is one of the factorization. So we'll factor these matrices. For example, if we have a matrix A which is diagonalizable, so we'll have something, for example, S lambda S inverse, something like this. So this is one matrix, this will be other matrix, and this will be other matrix. So this is also a decomposition. Let me motivate this example first. Why are they so important? So you might have heard about the recommendation systems. How many of you know about recommendation systems? At least have heard the name. Okay. So there was a really good challenge. So making a recommendation is a huge task. So if you see YouTube, Netflix, and even even Zomato nowadays, Flipkart, and every e-commerce website has a recommending system that's running on the back end. The whole job is that it should recommend the products that we like. In case of YouTube, it should recommend the videos that you would like to watch. Okay. So Netflix had a challenge. So Netflix gave a challenge in which they were offering $1 million. $1 million is a huge amount. So they were offering $1 million, and the problem statement was that the people who are solving this challenge, they should be able to make the Netflix system recommendation system better. Netflix recommendation system should be made better by some metric. Like there was some RMSE score, and they have to make it better. So what happened? And they released the data set. They released what is called as Netflix dataset. Netflix dataset. So it has like movies and the things like that in that. So see the price. They've offered $1 million for the people who will make their recommendation system better. Then there is a team who solved it. They named themselves as Ensemble. So this was a team's name. So this team came up with the algorithm. They called it a collaborative filtering algorithm. Collaborative filtering algorithm. Okay. So in this algorithm, what they did is, so they have an assumption that similar users will have similar preferences. So that means like if two users are somewhat similar, so we'll recommend the similar items to them. Let's suppose Jahangir and Amir are somewhat similar to each other. So in their preferences, because maybe their age is similar, they live in the same area, and maybe they are friends, and they have a lot of similarity between these. Maybe whatever the Amir will like, probably Jahangir will also like the same thing. So the assumption here was similar users will like the similar items. So they made the Netflix algorithm better by better by maybe some point something, I think. So and they won the $1 million prize. So they won $1 million prize. And what is the technique they use? That's called as collaborative filtering. In that they use matrix factorization. So whatever you are going to teach this, whatever we are going to learn now, whatever I am going to teach now, it basically won a $1 million prize in the Netflix challenge. So again, an interesting story to add this upon. So when they released this data set, okay, so what happened at that time? My advisor's advisor, my grand advisor, his name is Pandurangan. So he's a really great computer scientist. So he had a student that time. His name was Arvind Narayan. So his name was Arvind Narayan. So what he did is he took this data set and he de-anonymized it. So they have anonymized the data set so that that people could not see who are we talking about. Say they performed something called as they performed statistical analysis and reconstruct the whole data, and they were, I think, able to identify it more than 80% of people uniquely, and Netflix had to take the data set down afterwards because there was a huge breach of privacy. Breach of privacy was there. So for that, Netflix had to take the data set down. And this guy is now a professor at Princeton, this Arvind Narayan, and he and I shared the same advisor though. And I worked on this problem. So what I worked in the major part of thesis was privacy preserving recommendation systems. So I was working the recommendation systems, but for this problem, so that the data should not get leaked, and there we use something known as multi-party computation. Maybe someday we'll talk about that. But do you got the at least some notion why are these things important? Why is algebra important?
Yes, sir.
So this was a little backstory which I wanted to share with you so that at least it motivates the example. So why are we doing this? So now we are going to see diagonalization. This is one of the matrix factorization methods. We'll maybe learn at least 4 or 5 methods. So I'll start with this, and then I'll probably cover some other sections when we'll be done with the eigenvectors and eigenvalues. After that, we'll take these matrix factorization separately. So now what is this diagonalization? So if we have a matrix A, we can represent it using S, lambda, and S inverse. Now I'll tell you what this S and what this S inverse means. So the assumption here is that, let's suppose this A, it is an n cross n matrix. This is an n cross n matrix. Okay, and then it has n eigenvectors, and they are linearly independent. They are linearly independent. I think you know the meaning of all the terms by now. So what is this diagonalization theorem saying? It's saying that if we have a matrix n cross n matrix in which we have n vectors which are linearly independent, then for that matrix we can write this A matrix like S lambda S inverse, or we can say S inverse of AS is basically equal to lambda, and we'll see what this means. So in this S, we'll basically put all these eigenvectors. Let's suppose eigenvectors were u1, u2 till un. We'll put them as columns. So this is how S is defined. Okay, this is what S is defined as. So this is equal, or we can take this equation or this equation. These are one the same. Okay, so this S is the equation in which we'll have these eigenvectors, which will be just as the columns of that matrix, and S inverse is the inverse of that, and A is the original matrix. So if you see the factor, this is the factorization. So this is S lambda and S inverse. So now I need to prove this. And now first you should be clear with this. So assumptions basically are, we have an n cross n matrix which has n linearly independent eigenvectors. Let's call them u1, u2, and un. These are linearly independent. That means, so you cannot take any linear combination and produce any other vector within the set. Or that means if you take any linear combination, that will be equal to 0 for these coefficients, non-zero coefficients. Okay, so now I'll tell you what this means. So I'll try to prove this property. Okay, so what I'll write is, so if I write this S, so this S basically is now u1, u2, and so on till un. Okay, this is S. Let me write first this. So after that, what I can write is this lambda basically is this lambda, big lambda. So it is a diagonal matrix which has the values lambda 1, lambda 2, and so on till lambda n, and everything else is 0. It's a diagonal matrix. So here we have the S inverse. We have the inverse of this S inverse is here. So then now let me prove it is equal to A. I need to prove it that this is equal to, this actually is equal to A. So we know that AX is basically equal to lambda x. Or let's say, suppose here we have taken AU. So AU1 will be equal to lambda U1. Similarly, AU2 will be equal to lambda U2, and till AUN will be basically equal to lambda UN. This is by the definition of, this is by definition of eigenvectors, what eigenvectors are. Okay, if you agree with this, so what I'm doing is, I'll take this A like this, and this and I'll club these matrices together. So this I can write like this S. So S here is, if you just expand this one, so S here is u1, u2, and so on till un, like this. This is this S. So I'm just writing it all together. This A will be separated out, and this matrix u1, u2, they will be separated out. So what I'm telling you that is, so here, so let me just write it clearly. So I think first we should look at an example, then I should provide a proof, or we can do the other way around. Okay, that's it's basically the things are similar. So these are the vectors now. So now what I'll do is, just take it as it is. So this is AS. So what I'll write now is, so this is u1, u2. So I'll just multiply this with lambda. So lambda here is equal to lambda, and it will be lambda 1, let's suppose u1, plus not even plus, so we can just write it separately. So if you want to write, so this will be lambda 2 u2, so a matrix basically, something like this. If you just collect all these things into a matrix, this will be lambda u1. So I'll just write it like this, lambda, this should be 1 2 1 2 3 and so on. So here we have lambda u2, Similarly till lambda un. So we have this U's. Let's suppose we'll have this A and S matrix that you know that's equal to this. Is it clear? So A and S matrix is this. So now what I did is I just took these lambda 1, lambda 2 and lambda n, I just clubbed them and I made a matrix like this. So what now I can do is that this A S is equal to, so I'll just take these lambdas out. So it will be like this. I'll take lambda 1 here, lambda 2 here, and all the entries will be 0 till lambda n. Then again I can write it like this. So here I can write it like u1, u2 till un. So if you just perform the calculations back, so you see this lambda will get multiplied by this u1, then this lambda 2 will get multiplied by this u2. So again we'll get this matrix back. So basically from this we arrived at here. So from this we arrived at AS, and from here we arrived at this lambda 1 u1 u2, something like this. So now this matrix is now basically equal to S. Okay, so this means A S is equal, let's call this lambda matrix a big lambda matrix, and this is equal to S. So now if you want this A matrix, apply the S inverse onto this side and onto this side. This should be, I think, so sorry. So actually this should be multiplied on the right hand side. So it should be the other way around. It should be like this. It should be u1 here, u2 here till un, and then lambdas will be here, lambda 1 till lambda n. This order will get reversed, sorry for that. So here we'll have this S and lambda matrix like this. So now what we are doing is we're applying the S inverse onto here. So we had equation AS is equal to lambda S lambda. So here we'll apply inverse on the both sides. So this will become identity. So now we have A is equal to S lambda S inverse. So this is called as the diagonalization. Again, to show you the proof, so we have, this is the equations that we described. So I told you that we can collect this A and this S separately. Then you know that this can be written like this: lambda 1 u1, lambda 2 u2. If you just club them together in a matrix, so that matrix can be shown like this. So if you separate them out, so this whole u1 will get multiplied by this lambda 1s, and then the first row basically will, the first row of this will get multiplied with this, and you can even call that linear combination also. So you will take this and then it will get multiplied with whole of this u1, giving you this one, and then similarly you will take the second entry lambda 2 over here, this will get multiplied with this thing, okay, to get the columns of this. So basically you know that the columns of this or the linear combination of columns of this. Okay, so that's why how I wrote this. So this matrix I called it S, and this matrix is capital lambda. Is the proof clear? Maybe we'll go head up with an example and then maybe it will
Yes, sir.
If the proof is clear, let's suppose we have a matrix A, which is let's take some matrix 1506. Let's suppose this is the matrix, and we want to show its diagonalization process. So what we're trying to do is we're trying to decompose it. We're trying to factorize it in some other matrices. So again, see the magic of factorization. The thing is, like, what you can achieve with different things, you can achieve with the one thing. So I might have even told you when we were doing matrix multiplication, AB is equal to C basically means that whatever you can, you'll apply first this transformation B, then you will apply this transformation A. So whatever you can achieve at this, you can achieve that by only one transformation. So in the similar fashion, if you are decomposing a thing, decomposing means C is equal to AB. So whatever you are achieving with C, you will be achieving with apply B first and then A first. So you'll be achieving that thing with this C altogether. So that's the point here. So A here is a matrix. So the assumption here is that all the eigenvectors basically should be independent. So if you compute the eigenvectors, so let's compute the eigenvectors. I think it's easy for us to compute the eigenvectors now. So determinant of A minus lambda I should be equal to 0. So that means 1 minus lambda, 5, 0, 6 minus lambda, these should be equal to 0. Let's multiply this, and I have pre-computed the values. So the eigenvectors of this matrix A is basically equal to 1, 0 and 1, 1. So these are the eigenvectors. So eigenvectors of A. These are our eigenvectors. Okay, and corresponding eigenvalues are 1 and 6. Why are the corresponding eigenvalues 1 and 6? Can somebody tell me why are the corresponding eigenvalues 1 and 6? So eigenvalues are 1 and 6. If you just remember the properties, I told you that this is a triangular
Yes.
matrix. So in that, the eigenvalues are directly diagonal entries. Okay, so here the eigenvalue vectors are these two, and the eigenvalues are 1 comma 6. So now we need to basically, I showed you a generic proof, and for one example I'll just show you that this follows. And now if you take the x inverse as well, so x, or maybe a inverse we call it. So a inverse, if you take inverse, that's pre-computed for me, so it is 1 minus 0 and 1. This is a inverse, and a here we had 1506. This is all the details that we require. So now if you see this, so if you take a, so a here is 1 minus 1, 0 and 1. This is our a. Let's see if it is equal to the s. So this is our, so we can make s out of it. This is our s. Okay, this is our, let's suppose s. I think this is our s inverse. Sorry, this is not a inverse, this is s inverse, because we need that s inverse. We don't need a inverse. This is s inverse. So here we have this s. Now we have s inverse, and we have a, we have corresponding eigenvectors as well. So we know that this a is basically equal to s lambda times s inverse. So let's write this s. So this s will be equal to this 1 0 1 0 1 1. Okay, so this is the s, and then lambdas will be equal to 1 and 6. 1 and 6 will go here, then zeros over here. This is our s, this is our lambda, and then we need s inverse. So s inverse is 1 minus 1 0 and 1, and we need to verify is this right. I think theoretically we showed it is right. To just convince yourself, so you'll have to do this. So let's first multiply these two matrices. So if you multiply these two matrices, so this basically says take one of this column and none of this column. So first column will be 1 0, then take 0 of first column and 6 of the second column. So this will be 6 6, and then the other matrix 1 minus 1 0 and 1. So take one of the first column from these two matrices, take one of the first column, none of the second column, and minus 1 times and 1. So that is 5, and then we have 6. This is the matrix that we had. Oh, it should be a, sorry, this is a matrix. Our a matrix is this 1506 1506. So we got that 1506. So we got this a is equal to s lambda s inverse. So is it clear now? So is the process of diagonalization clear?
Yes.
So how do we diagonalize? Now we need to see some important properties for the diagonalization, and then I'll make some points regarding it. So we have this as is basically equal to s lambda. Okay, so s inverse a s is equal to lambda. That's what we got. So let's suppose we'll take this one and we'll multiply the matrices. Okay, so what I'm doing is I want, why is this diagonalization important? That I want to show you. Why is this diagonalization important? So if you have this a now is equal to s lambda s inverse from these equations. So this is the first equation. From this we can get this, and from this we can get this. This is the most important thing that we want to remember. So let's suppose I want to find a100. Okay, if you want to find a100, because computer science students, being computer science students, we are worried about the complexity. Okay, and you know that matrix multiplication can be done in with an order n cube complexity. If you know what complexity means, it's like order n raised to power 2.5 or 2.6, but let's suppose this is order n cube. And if we have this let's suppose 100 powered matrix, so it's a really tedious task to perform, so it will take a lot of time. So if we have a matrix which is diagonalizable, so look at the neat fact that we'll get out of it. So let's suppose we write a multiplied by a. That basically means s lambda s inverse. So for this s lambda s inverse, then again for this s lambda s inverse. So these two will become identity. So here you say that s lambda 2 s inverse. So a square basically is this. A square is s lambda square s inverse. So similarly, if I do it for cube, a multiplied by a multiplied by a. So that will be s lambda s inverse, s lambda s inverse, s lambda s inverse. So again, if you see, these two are identity, these two are identity. So we are left with s lambda times lambda times lambda s inverse. That's s lambda cube s inverse. So this is a cube. Okay, so from this, what I can claim is I am saying that a k basically is equal to s lambda k s inverse. So if you have matrix A and that is diagonalizable, and that means you can find the eigenvectors, and you can find the corresponding eigenvalues. So first we will find eigenvalues and corresponding eigenvectors. If you have these two things, then you don't need to even multiply the matrices. You can just raise the eigenvalues to the power of k and then apply this S and S inverse onto this to get the value of this AK. Is it clear?
Yes, sir.
So you saw the power, like one thing which these diagonalization process is there for. So this is a neat fact that you need to sort of remember. This is again a good fact because sometimes you will be asked a question to write a program for this, and that you have to see that time. Should I even apply multiplication or should I do this diagonalization? Because you are basically dealing with complexity. So if the because computer science students, being computer scientists or computer science students, what we are worried about two things. We are worried about resources in terms of CPU time and in terms of memory. If there is an algorithm, how fast does it run? That's the first concern that we have. And the second thing is how much memory does it take? That's the other concern. So if you are given a problem, you are told, okay, this is the problem, and you have to, let's suppose, find a to the power 100, and you're finding some pattern in that. And the first thing a normal computer science student who maybe knows some coding, and he'll just try to multiply these. He'll write an algorithm for matrix multiplication. Let's suppose definition, he'll write matrix multiplication and give two arguments, let's suppose a and b, and maybe write a lot of code and return at the end matrix multiplication of a and b. So what he'll do, he'll call this function recursively. So he'll call this function, let's suppose, 100 times to do this, and then see the memory it takes. The first thing is it'll take him 100 calls to do it. And the second thing what he'll do is he'll have to within the matrix multiplication he'll have to write the loops and things like that, and it'll take a humongous amount of time and the resources as well. So if somebody knows a lot of little bit about the this little bit about the linear algebra and the math, so what he'll do is, so probably if he finds this as the best thing, so he'll probably diagonalize the matrix. So if the time of diagonalization is less, if it takes very less time to diagonalize the matrix, okay, then what we can do is we can just take these eigenvectors, make it into a matrix, then have just perform these three matrix multiplications. This is just one and two matrix multiplications. The additional thing that we have to do is, so in the first thing we can do, we can perform 100 matrix multiplications. There are 100 n cross n matrices, and we are performing 100 matrix multiplication. In the second case, this is the first case one. In the case two, what we are doing is, so we are taking the matrix and we are diagonalizing it. We are finding the lambda 1 till lambda n. This is the first step one. And then in the step two, we are just performing three matrix multiplication, because we are finding this lambdas and eigenvalues. Correspondingly, we will get eigenvalues. This is the first step, and then we'll perform this S multiplied by lambda and S inverse. This is what we'll perform to get that, maybe for, let's suppose, a 1000 or a hundred maybe for here. So, and we'll have to analyze. This is what is called as analysis of algorithm. So you are building an algorithm, and that time you want to save the resources in terms of CPU time, in terms of how much time the algorithm takes, and in terms of memory, how much memory it takes. So you must know these techniques in order to write an optimized version of code. Okay, I think I made my clear point from the computer science perspective as well. Okay, and if you sometimes want to get this, if for example you are saying, does this AK go to 0? So if somebody says you, okay, if I keep on multiplying A, let's suppose I have some matrix A1, A2, A3, and so on till, let's suppose, some B and something like this. So I have some matrix like this. So somebody tells me that I'll keep on raising it to the power 1, 2, 3, 400. So will it go to 0 sometime? So how to confirm this? So what you can do is, you can say that, what you can do is, you can say, as I know that if this matrix is diagonalizable, so AK is basically equal to S lambda times K S inverse. So if all of these lambdas, all of the eigenvalues basically are less than 0, so for sure it will go to 0. Because if it is, for example, it's less than equal to, I think not 0, it's less than 1. So let's suppose we had 0.2. So if you take it to the second power, it will become 0.04 or something like 0.04. Then it'll keep on reducing. This value will keep on reducing till this k goes to infinity. Okay, so if you have a number which is less than 1, and you keep on continuously raising it to the power, so then it will go slowly towards the 0. So in order to confirm this, if this AK, if a matrix AK goes to 0, if I multiply it, and why is it required even? Why is it sometimes required? So in the machine learning, there is something called as a vanishing gradient and diminishing gradient problem. So there you will have to see, if I perform these multiplications, if I have very small numbers, So if I perform these multiply, because in the gradients you'll mostly perform these operations, you'll multiply, you'll do something with numbers, and there the whole thing will go to 0. Okay, so you might be thinking that why am I getting this 0 as an answer? So the thing that time will be, maybe you are raising it to, you're multiplying it quite enough, and that time you're getting it towards 0. So to confirm that, you can just diagonalize the matrix and see what are the eigenvalues. If you feel that these eigenvalues are less than 1, so that time you can confirm that this is why it's happening, because this matrix was such that if I keep on multiplying it, let's suppose for 100 200 times, I'll get the value ak as 0. Ak will be approaching 0 if this k is approaching to infinity, but the condition is that these lambdas, they are less than 1. So these are small things that you need to take care of. That's what separates a good computer scientist from maybe a computer programmer, because a computer programmer can write code, but who writes the better code is the question. The question is that, can you write better code? By better I mean, can you write optimized code, and do you know what is going underneath the hood? So can you change it? Do you know how you're utilizing the resources? Are you just using the things and you are overutilizing the resources? Maybe you can make a beautiful game, but the thing is that won't be deployable. So even I know problems what's happening with the Samsung right now. So Samsung has to deploy some machine learning models. So but it's taking humongous amount of energy. Why is it taking energy? Because the operations that it had, it is taking a lot of operations, and because of the operations, it's taking a lot of power. Now you see a mobile phone. Your mobile phone has a small battery in that. So, and you have the limited power to that. If you sort of keep on doing this, if you drain the power because of the ML algorithm, let's suppose I'm writing on this tablet, and this there is a model deployed under it which recognizes the digits. So if I write, for example, ZEBR is zebra, and here they have an algorithm. For example, if I just write this, so I have selected this much. So if you see over here, it got converted into zebra. So I just took this A, and there's this much. Are you able to see the zebra over here?
Yes, sir.
So they have deployed basically a machine learning algorithm there, which is recognizing digits, which is recognizing this handwriting. So let's suppose I'll write something else to confirm it. For example, Samsung. Okay, so I'll just apply on this. So this basically recognizes the digits. Do you see Samsung over here? Yes. So if you see
Oh,
it, so they have actually, what is happening is they have deployed an ML algorithm, but that ML algorithm is now capable of doing this. But on what cost? The power consumption should be very less. So for that, in order to create those optimized models, you must know all of these things that's going around. कि बैटरी का कंजप्शन बहुत कम होना चाहिए, not like you will not use battery, but try to make it as minimal as possible. Then you might be seeing the problems with, if you are using these 4G phones, they sometimes heat up while you call. They heat up. Why do they heat up? Because they use something called as, if I'm correct, they use something called as packet switching. So what is that? So what is this packet switching basically is, you will send the packets out of order. So when it gets to your phone, so then your phone has to assemble those packets together. Okay, then it assembles and it does some processing. So phone does some processing. So phone has to process. So if phone has to process, automatically it will drain battery. So that's why these, maybe for example, if you have these VoLTE calls, voice over LTE calls, so these phones become warm a bit, and they dissipate heat, and at the same time they also give very less battery time. And if you see those 2G phones, keypad phones, while you use Nokia use something called as circuit switching. So circuit switching, what it does is, it even sends the packets in the order. So that time you don't, in the phone you don't have to assemble. So if you don't have to assemble, whatever comes out of there, you'll be able to hear that. That's why sometimes there's a breakage of the audio. So what breaks, you cannot assemble it. But nowadays in WhatsApp, if you see, WhatsApp also does this voice over this IP. So what they do is, they'll send the packets and probably they'll assemble it together, and maybe there will be a delay in voice sometimes. So what happens is, if some packet is not reached yet, so others will be waiting for that packet, and then they'll assemble it in order, and then you will listen maybe audio after 1 second or 2 seconds. But that processing is done by the phones, and that's on cost of the battery. So now we are assuming that we have enough battery in the phones and we can deploy these. But seriously, there are some applications in IoT device and stuff where you have to take care of the batteries. Why am I dragging you into this discussion? Because that's the point we are sort of learning all of these concepts. It's not just you will apply some machine learning model. You must know, as a good software engineer, as a good data scientist, that what is going on in the hood, how much power is consumed, and how much what is the because power consumption is directly it's directly proportional to the how much operations are done by the algorithm, and that is directly proportional to even what are the algorithms that you are using underneath. Is there a scope of optimization? So am I clear with this discussion? Okay, so now you understood the process of diagonalization and you saw that how, where can we use this. Okay, and now we'll move on to some other things, that is we'll see what which matrices are diagonalizable. So the question is, which matrices are diagonalizable? This is the question at hand. So let's suppose that matrix is A. I'll write a statement, just read it and see it through. So A will be diagonal if it has n independent.
Sir, is recording going on?
Yes, 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 it is going on.
Okay.
So what I'm saying is A is diagonal that if A has n independent eigenvectors. Okay, that means, so what is the implication of this? The implication of this is that if there are some there should be lambdas which should be different. So eigenvalues should be different. And you saw the case where the eigenvalues were similar. So if you have similar eigenvalues, you will get similar eigenvectors. Okay, so for sure we will say that this A is diagonalizable if all the n independent eigenvectors it has are independent. If it has n eigenvectors and they are independent, and from this I can say that there are no repeated eigenvectors, no repeated lambdas. So this is a short thing, but sometimes there may be repeated eigenvalues. Still, that matrix will be diagonalizable. Let's suppose we'll take example of identity matrix 1 0 0 0 1 0 0 0 1. This is the matrix. This is an identity matrix, and you know that the lambdas are all equal to 1. But you know that we can take any three vectors 1 2 3, 1 0 1, 4 1 2, something like this. So these are three vectors, and I think these can be considered as eigenvectors. So everything with respect to this identity matrix is an eigenvector, because this is, let's suppose A, if you multiply any vector x, you will get 1 times that x. So any vector for this identity matrix is actually a eigenvector. So what I'm telling you is that if there are repeated lambda, so we are not sure whether this matrix will be diagonalizable or not. But the thing is, we'll be sure that if all lambdas are different, if there is no repeated lambdas, if you have a matrix and you found that the lambdas over there, all things are different, there is no repeated values, so for sure you can say that A is diagonalizable. But the converse is not true. So the converse basically means if all the diagonals are similar, you cannot say whether is it diagonalizable or not. It may be diagonalizable and may not be, that you have to check. But for sure, if you have a matrix in which all the lambdas are different, no lambda is repeated, that time you can surely say that this matrix is diagonalizable. You can diagonalize that matrix. Okay, and repeated eigenvalues. So for repeat, I'll just write it. So for repeated eigenvalues, it may or may not be diagonalizable. Okay, but for sure, if lambdas are different, so if lambdas are different, that means eigenvectors will be different. So for sure that this will be diagonalizable. Okay, now what is the process? So if you want to find the vectors, the process is that you just take this matrix A and you solve its determinant of A minus lambda I, and this will give you basically the value of lambdas. This will give you basically value of lambdas, and from these eigenvalues compute eigenvectors, and then collect these eigenvectors into a matrix S. Let's call these eigenvectors u1 u2 till un, and these lambdas collect them into a diagonal matrix. This will be lambda 1, lambda 2 till lambda n, and now you know that A is equal, just find the inverse of this also. So this S, lambda S inverse. This is how you will diagonalize a matrix. But for that you will get a surety over here. For example, if lambdas were different, so you are sure that these basically all the eigenvectors will be independent, and they will be basically different. By different, I don't mean just different. Difference, I mean that they'll be in the different directing towards different planes. Okay, so what is the application of this? It has got a lot of applications. So I'll just mention the applications so that you will go and look at these applications, because otherwise I'll just take maybe 2-3 lectures to just cover the applications of how this diagonalization is used. The first application, for example, if somebody tells you compute the 100th Fibonacci number, there is one process iterative loop that you saw. Even you guys saw that how to from the iteration how to find that. So what you did is, so you know that Fibonacci number f of k is basically equal to f of k minus 1, f of k minus 1 plus f of k minus 2. Okay, this is what the Fibonacci number series is. So that's 0, 1, 1, 2, 3, and so on. I think you have solved this question in the assignment. Have
Yes,
you?
sir.
Yes, huh?
Yes, sir.
So now the applications also include, now without even this, without even using this recursive approach, without even using this, can you use this algebra? Can you use the algebra to find, let's suppose somebody says you find that 1000 Fibonacci number. Will you be able to find it? That's the question. So if you were able to find it, by it, here you will apply the diagonalization process. Okay. For example, if somebody gives you, if you know about compound interest, so how this interest works. So I think Einstein said this is the eighth wonder of world. There are seven wonders. If you see the effect of compounding, this is the eighth wonder of world. Let's suppose you have some principal amount, and then there, annually you'll get some returns onto this on your principal amount, and now you have this compound. Then the principal plus this interest becomes the new principal for the next year. Okay, and it again is a recursive sort of thing. So it again recursively happens. This also we can use diagonalization onto this. You can use diagonalization for computation of the compounding also. Okay, so I gave an example of Fibonacci numbers, compounding, and you can also, you know what, you can also solve differential equations. So you can solve differential equations by using this. I wish that I had time to explain you all of these things, but I don't think that we have time. But these are really good applications. I think there are more lot than this, a lot of applications than this. I just showed you the three applications so that you will look on these: how to compute Fibonacci numbers by using this diagonalization, how to compute the compounding by using this, and how to compute the answer to the differential equations by using the diagonalization. So this is homework for you guys. So this is homework for you, and you will have to see key what are the applications and how to use these things. Am I clear with this? Now we'll move on to symmetric matrices. Symmetric matrices. We have covered these. Now we want to see them in the light of this eigenvalues, eigenvectors, and what is so special about them. Because I told you these matrices become really special. These symmetric matrices become really special. So what's the definition again, to sort of just brush up the definition? If we have a matrix A, if we transpose this matrix, that will change the rows into columns. If these are equal, then we call this matrix as symmetric matrix. Okay, this is a special matrix. This symmetric matrix is really special. Why is it really special? So if you see, if you have this matrix, let's call this now S. If we have this S matrix as symmetric matrix, and now you know that if we write Sx is equal to lambda x, because it will also have its own eigenvalues, its own eigenvector. So we can write Sx is equal to lambda x. So let's suppose x is a vector, and this is eigenvector, and this is its eigenvalue. So what is so special about this is that it has two important properties. The two important properties that I'll mention is that the eigenvalues are real. Just underline this, real. Maybe enclose it in the box. So the eigenvalues for this are real. So I even showed you the examples where the eigenvalues are complex. I think that I hope that you remember that case when we were handling that previously. So these matrices are special because the first thing that they have got is the eigenvalues for these will be real. They'll be real numbers. The second thing they have got is, the second thing they have this, the eigenvectors, the eigenvectors are perpendicular. So whatever eigenvectors you'll be getting, so they'll be perpendicular or the orthogonal to each other. So if you have this S matrix, so this is the symmetric matrix, and let's no, it should have been better to write it some other. Let's suppose this is S dash. The symmetric matrix is represented by S dash. So I'll just write it over here. This is symmetric matrix because we have used S also for those eigenvectors. So I don't want to overload the symbols. So this is our S, which we have the collection in which we put these eigenvectors. Let's suppose we have x1, x2 till xn. This is our S matrix for this S dash. S dash is symmetric matrix basically. So what I can claim is this: if all of these are orthogonal to each other, if I normalize them, so they'll become orthonormal matrices. So this S matrix will become orthonormal. So what is the property of orthonormal? So you know that S transpose is equal to I. If S is orthonormal, or maybe orthogonal only. So you know about this property. So that if S is orthogonal. So S transpose is equal to I. That time I also told you that S is equal to S inverse then. So from this it directly implies that S is the S is S inverse itself. So that's the implication of this. So these are two beautiful properties of this. So now you know that the singular value that the diagonalization that we saw is that if we have this matrix S dash, this is a symmetric matrix. So this basically is equal to now S lambda S inverse. If you see this, okay, if you see this is equal to S inverse. Now you know that I can just replace this with Q, because now I know that these matrices are orthogonal. So I can just write it Q lambda. I think this S should be S transpose is the inverse. Sorry, here S transpose, because S transpose is the inverse of S. So that's the meaning of this. So I can write it Q, because we have represented Q as orthogonal matrices lambda. So I can here write as Q inverse. So I know that this is equal to Q lambda Q transpose. That is for the symmetric matrices. And this is a good property, and it'll sort of boil, it'll just remove the it'll again make our calculation so easier. So that's why we're taking these things separately, so that we'll see why they're so special. And in the machine learning, you'll see many of the metrics are symmetric. But let me just give you the example. Just remember the names. There's a matrix called as covariance matrix. Covariance matrix. So this is a symmetric matrix. This is a symmetric matrix. So you can directly write it in this fashion. S dash, if this covariance matrix will denote that time maybe with C, that C matrix can be written like this. So why will we use this covariance? This will be used in principal component analysis. Then I'll say you this is a covariance matrix, and we'll take its eigenvalues, eigenvectors. Now you have the background. What is an eigenvalue? What is this symmetric matrix? What is so special about these symmetric matrices? So that time it will be easy for you to understand the mathematical details underneath. Okay, so that's what I'm telling you. So this S dash, and now I can claim this is if it's a symmetric matrix. So I'll just write this as Q. Q means it's an orthogonal matrix, or maybe orthonormal, because we can just normalize the column, then lambda Q transpose. Just remember this thing so that you do not confuse. So this S dash is a symmetric matrix. I just made it explicit over here. And the first thing is, we'll have to prove its eigenvalues are real. We'll have to see how its eigenvalues are real. Maybe I'll like to show you a proof. It'll just take me a couple of minutes. So I need to prove the first thing. Its eigenvalues are real. Let me prove that thing. Okay, what I'll do is I'll write the proof here. Proof eigenvalues of this symmetric matrix S dash is a symmetric matrix are real. Why am I showing you the proofs? Why am I showing you? Sometimes I'm showing you proofs, sometimes I'm giving exercises. I want you to sort of have that nature. Again, a digression I'm taking. Maybe it will be a 5-6 minute like. Should I pause the recording though? Whatever you say. If I pause the recording. So I am again taking a digression for this. Why am I showing you proof sometimes? The whole point is, most of you guys will be doing some things. For example, if you do competitive coding, there you will have test cases. There you have test cases. So you will just do testing. This is a digression. I'll just write it first. So if you are doing competitive coding or solving some problem, and you see test cases, if is it solving or not, and that time you will be feeling, okay, I have these test cases. If 10 test cases are passed, maybe it's a good enough algorithm. It runs. But in computer science or in general, we say proof by example is not a proof. Proof by example or examples is not a proof. So if you have to prove something, so he should not produce examples. So he should give a generic proof. So if I give you examples, maybe it works on 2-3 examples, but after that it will violate the law. It will violate whole of these rules. Maybe I had a good example. If I just remember that, some n square plus maybe 39 is a prime number, something like this. N plus n is a prime number. Not even 13, this is 41 maybe, is a prime number. Let's see. If I put 1 over here and 4, let's suppose n square. This is 1 square. No, I don't think like there is an example like there is a good example. So it follows if you give 20 examples, that thing will come up to a prime number. I have to see the expression. So if you put the values of n there, and you will see for the 20 values it will come out to be a prime number. But for the 21st number it won't be a prime number. So that I can establish that proof by examples is not a proof. Why is it so? Because if you see the first problem that happened, it was because of computer science. So you know about there was an Airbus. Okay, what happened in there? So they have used a code in Airbus which was used previously. So they just took the code and deployed on that machine, and the machine was running. So they have used, I think, 16-bit register. In the previous code they use 16-bit register. So you know that the range of values is 2 to the power 15 minus 1. So it was having a counter or something, and it was counting. And for the previous machine, it never touched this range. So for the next machine, they said this code is running. We don't need to again refactor or look at the code and give the proof. We'll just deploy it to the next Airbus, and we'll just get it flying. So what happened that time is, so when they did it, and at the counter basically went out of this range. So there happened something called as overflow. So when this overflow happened, that time the problem was, then they had like I think nearly millions of dollars were they got destroyed because of an programming error. Now whatever you write in the code, so there you will be asked for the proof. You'll be asked, okay, write the proof for this algorithm works. So for the algorithms, there are different proofs. So you have to learn about loop invariants. If you are using loops in this, you have to write about these, and you will write proofs by induction, and you will write proof by contradiction. And even now there is a subject called as FMSE, formal methods of software engineering. They try to make such a program that it tests itself. So now we have to have testers in the programming, so which test it on the some test cases. But still we feel that maybe due to the human error, some tests might have, there will be some corner cases which humans might not be able to think. So that we should have a formal method, so that we can say that this algorithm is perfect. So that's where these proof techniques come in. Why I do teach you some proofs, why do prove things? Because you should have a habit of asking this question, prove this thing. If you are claiming that this should work, give the proof of this, and it should be a mathematical. It should not be a proof by example, or it should not be just a pictorial proof. Because in pictorial proof, it's really easy to make fool out of people. So let's now see the proof of this. So now you know that this ax is equal to lambda x. So the claim I made is that the eigenvalues of symmetric matrix are real. Okay, and the first thing is what I want to prove. I want they are real. So how to prove that? We should mathematically model it first. We should see mathematically. Okay, what I'm proving. So what I'm proving is, so there are real numbers and there are complex numbers. Okay, I want to show that these are not complex. So how to even prove that these are not complex? So first let's establish that thing. So if we have a complex number, let's suppose a plus iota b. Okay, if you take its conjugate, if you know its conjugate, so conjugate is written like this. So you just put a bar and you'll write a plus a minus iota b. So this is the conjugate. Don't equal. So this is conjugate. These are conjugates of each other. These here you're clearly seeing that these two are different numbers. A plus iota b and a minus iota b. So they are different. So if you have a real number, let's suppose you have a real number 2. So if you have its conjugate, so the conjugate will again be 2. So what I need to prove basically is, I have to prove that eigenvalues lambda is real. So I need to prove if I conjugate that lambda, it should be equal to lambda. So that is my proof that these are real. Is it clear that how will I prove that these eigenvalues are real? First, I need to see what I am going to prove. I am going to prove that these are real. So what I mean by real, I mean that if I take the conjugate of that number should again come to be the same. It should not be like the complex number. If I change the conjugate, the signs will get changed. It will entirely become a different number. Okay, for real numbers, the conjugate of a number is the same number. Basically, that's what I want to prove. So to prove here is that if I have lambda and I'll apply conjugate, it should be equal to lambda. That's what I have to mathematically prove. Now I have the problem. This problem was mathematically modeled first. Okay, this was brought in the mathematical world. Initially we had it in some world. I was using some words. I have to prove this is real. Now in order to do that, I mathematically modeled it. I told I have to prove this thing. I have to prove if I am having this lambda, if I apply conjugate onto this, that time what should happen? So the thing that should happen is this lambda bar or lambda conjugate should be equal to lambda. This is what I have to prove. Okay, now let's see how to prove this. So if I apply, let's say if I on for this equation, I'll apply x conjugate transpose on both sides. I'll apply x conjugate transpose. X conjugate transpose ax is equal to this lambda is basically a scalar, so I can take this like this x. So this is what I got after applying the conjugate onto this. So one more thing that I can do is I can apply the whole conjugate onto this also. So from this equation, the first thing is I'm getting this equation by applying x transpose. Now I also want to get one more equation on this. So I want to apply conjugate on the whole equation. That will be a x bar is equal to lambda bar x bar. Okay, I applied the conjugate on the whole equation. You know that if you apply conjugate on both sides, so they should be equal. So here that this a is real matrix. That's the assumption. Is a real matrix. So that a conjugate is equal to a basically. So that's why I haven't put conjugate onto this. So here these are the two things. So that I got from this. This is the first thing. And the second, maybe I'll just what I'll do is I'll again apply x conjugate onto this also. So what I'll do is I'll apply x conjugate ax, that's equal to lambda conjugate x conjugate transpose x. Huh. I think yes. So what I did is onto this equation. Oh, sorry. So onto this equation, I applied x conjugate over here, x conjugate transpose over here, and on the similarly I had this x conjugate transpose here. So now I am with these two equations. So you saw that I got these both equations from this. So here I applied conjugate onto the whole equation. I got this equation. So after this, what I did is I applied this on both sides. On both sides. Here also on both sides. So now if you see in the both equations, this left hand sides are equal. If left hand side is equal, that means right hand side is also equal. So that gives us this lambda x transpose x is basically equal to this lambda x conjugate x. So if you see that this and this get cancelled, so I proved that lambda is equal to lambda transpose. So that's the real. That means this eigenvalues of a symmetric matrix, eigenvalues of a symmetric matrix are real. Okay, is it clear?
Yes, sir.
So did I did some mistake? No, I think it's perfectly legit. Yes, yes. So this is what I had to prove. I think I did all the steps right, but still, uh, the doubt I have is my doubt, like how I'm thinking. My doubt is where am I using this A is equal to A transpose? Why am I using symmetry? I just proved it for the general case. I proved it for A. That's how your brain should think. But I proved something, but I had to use that this is a symmetric matrix. But I sort of I proved it for a general matrix. Now I need to show that where is the mistake that I committed? Is there a mistake even? Hmm. I think here I should have applied transpose on both sides. That will make this transpose, and this should be this is a applying conjugate onto this. Okay, this is good. This step applying conjugate onto this. So this seems good to me, and then applying x transpose on here, x transpose. See this shake. This step looks shaky to me. Just check it. Once you go through the recording, just check it, because I don't want to spend time over here because I just proved it on the fly. So here now I just sort of established this that eigenvalues of a symmetric matrix are real. I even told you what the doubt. My doubt is that why did I use 8 is equal to 8 transpose, and I think that should be used somewhere here in order to get this equation. And but the claim here is that the eigenvalues of symmetric matrix are real. That you have to remember. That's the thing that you guys have to live for. Okay. I think this is now this claim is proved, and I think we can also claim this. We can also so second claim that we had is second claim is that eigenvectors are perpendicular. So this is proof for you guys. So try to prove it. So okay, so I'll just mathematically model it for you guys. I'll mathematically model it. You want to prove these eigenvectors are perpendicular. That means what you have to show is you have to show if you take eigenvectors, let's suppose xi and xj. Okay, if you perform a dot product, that should be equal to 0. This is basically what you have to prove. So you will take any eigenvectors from this symmetric matrix, let's suppose S dash, and that will be, let's suppose xi you will take, or xj, separate eigenvectors, and this is what you have to put to prove will be this. And try to prove it, and try to also learn the proofs, maybe search it online, and then try to get hints. Do not even look for the proofs directly, but think about it, how to do these things. So I showed you that these matrices are special. So I showed you how they are special because they are orthogonal, and then there is a lot of computation that is being saved. And you will see that I will use these in PCAs and SVDs and stuff like that. Now I want to go again to a beautiful matrix which we will call as positive definite or semi-positive semi-definite, two types of matrices. But before I go to that, I'll just wrap this thing up with one more thing. Let's suppose I have this A is equal to Q lambda q transpose. This is for the symmetric matrices. So how I can write it? So if I have, let's suppose this u1, and maybe I have this u1 over here, I have this u2 over here, this is un. This is the meaning of this. And lambda basically means I have lambda 1 till lambda n, and then this q transposes u1 transpose, u2 transpose, and so on till un transpose. This is how actually in the matrix form that they'll be written. So if I want to expand these things, so what it will look like? So this will be something like this. This will be lambda 1, lambda 1 because it's scalar, you can write it anyway. You can write it any somewhere you want. So I'll just write it red, lambda 1, and this thing will get multiplied to this. So it will be u1 u transpose, u1 transpose plus then the lambda 2 u2 u2 transpose plus and so on till lambda n un transpose. So why did I write it like this? The whole point was because you see that these things we read about in the projection matrices. These are perpendicular projection matrices. So they are perpendicular projection matrices. Okay, so these are the things. So what I can write is I can write every symmetric matrix is a combination, basically every symmetric matrix is a linear combination, else linear combination of perpendicular projection matrices. Projection matrices. This is what I can claim. I just expanded the equation and I showed you that. This is what I wanted to show before going into those positive definite matrices. Is it clear so far? Is it clear? Guys miss it. So one more thing that I want to mention about these matrices is that signs of pivot is same as signs of lambda. Signs of lambdas. So what is the implication of this? So this implies that for the symmetric matrices, so if you see that all of these lambdas are positive, that means pivot values will also be equal to positive. Okay, so that means the number of pivot values is equal to number of positive values. Number of positive values. It's not for the real values. So just don't confuse the real and the positive. So what I'm saying is I'm saying the signs of pivot is the same as signs of lambda. So let's suppose you have n pivot columns. Those n columns will give you n lambdas. Okay, so I'm saying the sign will be similar. It's not the pivots will be similar. I'm saying whatever the sign of, let's suppose we had 4 pivot columns. Let's say 4 pivot columns, and those 3 were positive and 1 was negative. So what I'm saying is that I'm saying that 3 lambdas will be positive and 1 lambda will be negative. That's what I said. Sign of pivot is same as sign of lambdas. So whatever the sign of pivots is the same for these lambdas as well. You again need to prove it and just try to prove it. That means the number of pivot values is equal to number of positive eigenvalues. That's only number of positive eigenvalues that I want to show you before going into the positive definite matrix. Now let's move ahead with our probably the last topic, theoretical topic, and after that we'll take this SVD and we'll take the PCA. So that is positive definite matrices. This is what we'll take. So we saw symmetry. There are a lot of things to cover. There are Hermitian matrices. There are a lot of things, a lot of matrices to cover, but I think these things are more important. Again, I'll write some of the things that you have to cover on your own. Maybe Hermitian matrix you'll see, maybe Markov matrices. They have again some beautiful properties, but I don't think they come these frequently in machine learning and deep learning as these. These things you'll see frequently. These positive definite matrices, this and that. Why are they important? Why are they important? So because these positive definite matrix, so when you try to find a minima, so let me just explain you what is a minima and what's a maxima first, so that you get the context where are these positive definite matrices used. So in the if you see that linear regression algorithm that you saw, I told you that we have to minimize the error, minimize the error. Okay, that was there. We have to minimize the error. And when you will do when you will be doing some optimization problem, that time you will be solving basically a mathematical object that's called an objective function. So you'll be solving an objective function, and you will be asked to minimize the objective function. So maybe the objective function has some graph like this, for example, some graph like this, something like this, let's suppose. and you want to find minimum. Where is the minimum value? So for example, if you see here, they are called minimas. There are three important points. There is something called as minima, then we have maxima, then we have something called as saddle point. I just want you guys to know the name of these points. Maybe if you want to check the formal definitions, you can do that, but I just want to show you graphically. So this over here, if you see it, it's a minima. This over here is a maxima. Maxima basically means where is the maximum value attainable. So where is the maximum value? What is the maximum value of the function? Minimum value is what is the minimum value of the function. Okay. Then we have something called as global minima and local minima. Global and local. Global and local. I just want you guys to know these terms because we'll be frequently using them in the optimizations. That's why I want to leave algebra here so that I can pick up from the calculus from there. That I told you you should read the topics and stuff so that you feel need of going to the other topic. That's what I'm doing right now. So I'm telling you that these positive definite metrics, they are used in this minimization, maximization, and the saddle point things. So how will we using these positive definite metrics? We'll see that separately. But in order to motivate this, so I first am introducing some concept. Global minima here means, so what is the global maximum? That is, there will be lot of maximas. Lot of maximas will be there in a function. So if you see this is a maxima, if you see this is a local maxima, this is a local maxima over here. So out of these, probably, let's suppose this is the maxima out of all those maximas. We'll call this one as global maxima. These things will be local maximas. Similarly with the minimas, this is one minima, this is minima over here, this is minima, this is minima over here. Out of these minimas, this one is global minima, and this one is global maxima, and here they are local minimas, and these are global maxima. And what is the saddle point? In saddle point, it will be difficult in 2D to show you that, but I think you'll sort of see it. So in saddle point, what will happen is it will be like this, something like this. There will be a point. So in one direction it will look as the minima. In one, all these they are sort of, this is the unstable point, unstable. So let me again give you a physical example. For example, if you sort of have a ball over here, so it will be stable here, this ball will be stable here, so this ball will be stable here. If you just give it a little bit push, so this will land at this minima and it will be stable there. So they're also called a stable point sometimes, stable points. Why? Because of this property. For example, if you have a point over here, so it is stable here. If you just push it towards here, so it will go to the local minima. So again, if you push this in any direction, this will come back in the local minima. Okay. So here you push it towards here. What is the saddle point is? So saddle point has, for example, two ways. So if you just push it in one direction, it will go into one. It will go into one direction. It will go into the minima from one side, and from the other side, it will go to the maxima. So it is something like onto this. If you see it on 2D, so it will look something like this, over here. So if you just push it, it will go to this point. Let's suppose if you push it on this side, it will go to this point. Maybe I'll show you the graphs when teaching the optimization, but know these terms as of now. So there are three stable points: minima, maxima, and saddle point. So minima is the value of the function where it attains the minimum value, and maxima is where it attains the maximum value. So we have local minima and global minima. This is why these positive definite matrices, they are really important. So they obviously are positive definite symmetric matrices are more important. So what is the thing with this? So I'll write positive definite matrices, PDM. So they have some important properties again. So what is the important property? The first property is that all eigen values are positive. If you see in the symmetric matrices, there I told you that all eigenvalues are real numbers. There is no complex numbers. But as you know, these are symmetric matrices. So now the question is, are the values of lambdas positive or negative? So all these eigenvalues are positive. So the second property is that all the pivots are positive also. So all the pivots are positive. All the pivots are positive. So I told you that number of pivot, whatever the sign of pivot is, the same sign is for the eigenvalues. Let's take an example. Let's suppose I'll write an example. I'll write an example 5, 2, 2, 3. Okay, so we'll see what are its eigenvalues, and we'll see that. What is the pivot here? So pivot here is 5. This is the first pivot. This is 5. Okay, and what is the other pivot? So how can you compute the other pivot? So you will just subtract, and you want to make this entry 0, and you will see what happens to this. Okay, I think this should be 11 by 5. because you're multiplying this, and then subtracting with this. So this will be the pivot, second pivot. Okay, so these are two pivots, 5 and 11 by 5. So both of these are positive. So this we'll call this as a positive definite. And all the eigenvalue, if you see eigenvalues, and let's calculate the eigenvalues even. I think it will be determinant of a minus lambda I should be equal to 0. That gives us a minus lambda I, 5 minus lambda, 5 minus lambda multiplied by 3 minus lambda minus 4 is equal to 0. So I think lambda square, it is lambda square plus 34, and it is minus 8 lambda, I guess, plus 11. Just check it once. So this is the equation that I'm getting out of it. Then I can use that minus b plus minus 4 ac formula, quadratic formula. So lambda basically will be equal to 4 plus minus under root 5. So you see that these values are again positive values. So this is nearly less than 3. Is less than 4 easily, less than 3 this root, so it will be positive. So you see both of these lambdas are positive. So this is a positive definite matrix. Why? Because you see the pivots are 5 and 11. This is first pivot. When you will make this entry as 0, so what will happen? So this entry will get changed. So this entry will be changed to 11 by 5. So both of the pivots are positive. Just check the values when you are doing the calculation while making notes. And when you are finding this determinant, you see that when you are finding the determinant, and from the determinant you are finding the eigenvalues. So from that you see that these lambdas are equal to 4 plus minus under root of 5, and both of these are positive. So we'll call this matrix as positive definite matrix. Is it clear?
Yes, sir.
Let me just drink. Okay, now we want to see what are the matrices that are positive definite matrices. We want to check it. I'll first show the check, and then I'll show you like test for minimum as well, like how to find the minima by using these if there is a positive definite matrix, and we'll see that. The first, there are some checks by which you can see if this matrix is a positive definite matrix or not. Let's suppose we have this matrix A, which is A, B, C, and D. So what is the first check? The first check is pivots should be greater than 0. They should be positive. That means what's the pivot here? The guaranteed first A is the pivot. So A should be greater than 0. What's the second pivot? Second pivot is you'll have to make this entry 0. So you'll have to multiply this equation with C by A. You'll have to multiply this equation with C by A. Okay, so that this becomes 0. So this gets multiplied with C by A. Then this is D minus, if I am right, C by A. Let me. So this should be, the second pivot should be, this is AC minus B square. This is and the pivot. So these are the pivots. So this is the first A pivot. So when I make this 0, and this D will get changed, so this will become this AC minus B. This should be equal to greater than 0. And then we should have the lambda. So we'll have lambda 1 and lambda 2. They should also be greater than 0. Okay. So this is you can perform on the test. So this is one of the tests. So the first test is that you can just compute the lambdas. So that way you can say that this is a positive definite matrix because lambdas are equal. Or you can perform other test. You can just see pivot columns. So if these pivots are greater than 0, that's again another test. So what is another test? So the another test that we have is that basically is called a minimum energy equation. I don't want to show you that, but it's okay. I'll just defer it a bit. So first I'll write some other tests. So one more test is that all the subdeterminants, they should be positive. All the subdeterminants should be positive. They should not go to 0. Like for example, what is the meaning of subdeterminant? I'll want to show this. So first this A should be positive. Then whole of this should be positive. Let's suppose we have the 3 cross 3 example. A11, A12, A13 till A33. Let me write everything. A21, A22, A23. So by this I mean that this determinant, it should not go to 0 basically. It should become it should remain positive. And the second thing is this much, this should remain positive. Okay, and this whole should remain positive. That's what I mean by this. So all the subdeterminants should be positive. So if you see one determinant, for example, let's suppose if there is a 0 entry in here, let's suppose there is a 0 entry in the first pivot, that means it is not a positive definite matrix. So in order to check, this is the first check, this is maybe second, third, and let me write the fourth check as well. That's called the energy equation sometimes. So x transpose Ax is greater than 0. You'll have to check for this. So if you are given x, so we'll transpose that and multiply it with a to find x, and then we'll say if it is greater than 0, then it's a positive definite. Okay, let me give you a physical example so that you understand it. Let's suppose we have a matrix 2 6 6 over here, because it should be symmetric. That's the first case, it should be symmetric. So what should the entry, what entry should go here in order to, because the determinant should be positive. That's what you have to see. Determinant should be positive. So it will be like 6 6 36. So minus 36 we have. So here when we multiply this 2 and this number should be greater than 36. So if we put, let's suppose 7 or 8 over here, so 8 twos are 16. Okay, so see, it is not the positive definite matrix that time. So but if we put, let's suppose 18, it just misses it because it's equal to 0. We should put 19 over here. So now I'm so sure that this will be a positive definite matrix. Okay, so how do you even check that? So if we have this 2 6 6 and 18, so you know that now this lambda is equal to 0, this will become 0 that time. So that lambda is equal to 0, we call that a positive semi definite. Positive semi definite. So here we'll call this a positive definite. Positive definite. So if the eigenvalues, here I said that if eigenvalues are greater than 0, so strictly greater than 0, that is a positive definite matrix. If it is greater than equal to 0, some or zeros, in that case it is a positive semi-definite. Just remember this fact, it's a positive semi-definite matrix. So I think for this, the lambda, one lambda will be 0 for sure. The other lambda will be, so how to find this? The other lambda will be because sum of these things. So 18 plus 2 is 20, because you know the trace of matrix is equal sum of eigenvalues. So here one, if one is 0, the other should be 20. That is 2 plus 18 is 20. So these are the two eigenvalues for this matrix. 6 2 6 6 18. Okay, so what I'm telling you is that this is the most important equation that we'll check. This x transpose ax, it should be greater than 0. If it is greater than 0, it is positive definite. If x transpose ax is greater or equal to 0, then it is positive semi definite. Okay, so these are the two things. Now we will see. Let's suppose we have this x1 and x2. We have this vector x, that is x1 and x2. Now I want to see this, and I have a matrix A. Let's suppose that is our matrix 2 6. What I wrote, it should be 6 and 19. This is our matrix A. Now what I'll write is, I'll write x transpose A x. I'll evaluate this. This should be equal to x1 x2, and then A is equal to 2 6 6 19. Then I'll write x1 x2. Okay, is it okay? So now what I'll do is I'll just expand this equation. So if you expand it, so I'll first write x1 x2 as it is. Let me just write this one. So this will be one time of this column. So 2x1 6x1 plus 6x2 and 19x2. Now I'll again multiply this with this. So this will be, help me multiply, just check my calculations. So this will be 2 times x1 square. Okay, and then we have plus 2, this is 12, I think 12 x1 x2, and then this is plus 18 x2 square. 18 x2 square. Just check the calculations though. So now what I'm doing is I'm taking this and multiplying with this. So this should be 2x square, and then this should be like 6x square, like multiplying with this 6x square, and then with this x2. I think this is the equation. I think this is right. This is in the form, if you see, this is in the form of ax square plus 2bx some xy plus cy square. So this is in this form if you see this equation. So now I'll have to prove this basically is greater than 0 always. So now you know that this thing, so if you see this x square and s square terms, so these are obviously positive. They're always positive. If you give them some numbers, so they'll be positive. But the only dicey term is this dicey, this thing, this x1 x2. This is the dicey term that we'll have to check, and we'll have to see if it is greater than 0. So that we have to check if something makes it 0. So if we had that this entry, our initial entry, that we had this positive semi-definite, let's suppose less than even 7, if we had some 7 8 or 9 over here, then it will be easy. For example, if we have 7 8 or 9 over here, then it will be easy. For example, if we have 7 8 or 9 over here, then it will be easy. For example, if we have 7 8 or 9 over here, then it will be easy. For example, if we have 7 8 or 9 over here, then it will be easy. For example, if we have 7 8 or 9 over here, then it will be easy. For example, if we have 7 8 or 9 over here, then it will be easy. For example, if we have 7 8 or 9 over here, then it will be easy. For example, if we have 7 8 or 9 over here, then it will be easy. For example, if we have 7 8 or 9 over here, then it will be easy. For example, if we have 7 8 or 9 over here, then it will be easy. For example, if we have 7 8 or 9 over here, then it will be easy. For example, if we have 7 8 or 9 over here, then it will be easy. For example, if we have 7 8 or 9 over here, then it will be 7 or something like this. So that time what will happen is, so this will become negative for some entries. So now I will take the good case. Okay, so if there is a method called as completing the squares. So if you remember that method, I think it has been taught to you by in 12. So I'll maybe in +1 +2. So I'll directly write. So maybe I have to see the equation if it is right first. I think the equation is right. Yes, so I can graph this equation directly. Just check these calculations though. I want you guys to check these calculations. So you have to compute this. You have to basically just take the squares out of these, and it will be something like this: 2x1 square plus, let's suppose, something x1 x2, and then you'll have something like this. Uh, Maybe some plus some x, let's suppose y whole square, and here something will go into these terms. Okay, and but you know that now you have this square terms over here, so there will be some, again, some y square. You'll basically get every square term after this. You'll just write this in a plus b square format, and then you will write these coefficients. I don't want to do that because it will again take some time. So but here when you do that thing, so you'll be sure that all the terms here are now square. So that means that there is no chance that it will be negative. So there is no chance that it will be less than 0, because all the terms are square. So for all the values, then if you put any real number values, you'll always get the value greater than 0 for this equation. So if I evaluate this equation correctly, so just evaluate this equation for this value 19, and then just complete the square and see, you will get these square terms, and you'll be easily able to get this number greater than 0. Okay, so if I have to draw the graph of this, so there are x squares and y squares. If you see, so if I have to draw the graph, that graph will look like something like this. So I have my x1 and I have my x2, and I'll draw some graph. So this equation, that let's suppose that f of x maybe is like, that's equal to 2x square plus 12xy plus 20y square. Something like this will happen. So you see that this equation passes through origin, so there will be this origin if you see it, because if you put 0 over here, 0 for the x and y, whole equation will become 0, so it passed through origin. So if you see, this equation will become something like this, something like this. So it will be something like this, but it will be in 3D. So it will be like a bowl. So it will be like a bowl in which we have this minimum point. That's our minima. That's our minima, and we're interested in finding this point, this minimum point. So if you even see the calculus, so that's why I think I got the equation for the complete square. I am seeing it on the screen right now. So this is the equation for this: 2x plus 3y whole square plus 2y square. Just confirm it. So here you saw that now this term is square term. This term is also square term, and you got these coefficients. And these coefficients will be basically the pivot values. These coefficients will be the pivot values. Okay. So this is the equation after this completing the square of this. So this is if you just expand it, you will get this equation back. Okay, so the graph of this equation is this. So you need to find the minima. That's where this comes in. That's why these positive definite matrices come in. So why is the importance of the positive definite matrix? So if you now form this, you have to form a matrix in order to find the minimum of that. Because I won't show you how to solve the matrix, but still, so you will get something like this. Here you will have d by d square by dx square. Maybe I'll write it in the, this is called as Lebanese method. I'll write it in Newtonian method. So this is double derivative with respect to xx. So this will be double derivative with respect to yy, and this will be f of xy, and this will be f of yx. This will be a matrix. So now this matrix should be positive definite. Okay, so this should be positive definite, and in order to compute this minima and stuff. Okay, and then if you sort of have, if you just pass a plane through this, so you will get an ellipse. So if you have a bowl like this, you will have a bowl will be like this. Okay, and here we'll have minima. So if you cut down it like this, so you will just get a thing like this. That's ellipse, and this is the equation of ellipse. If you see in the first session, if you remember, this is the equation of ellipse. So this is our ellipse also. So you saw that to find the minima, to find these minima, so what we'll have is the only point, the thing we should have is we should get this positive definite matrix, and then we'll be able to easily find the minimas. So what is the condition for minima? The first thing is the first derivative. The first derivative should be equal to 0, and for the minima, second derivative should be greater than 0. It should be positive. That's what I'm saying. This is the second derivative. This fxx comma fyy, they should be positive. In order to have this positive definite matrix, then only we'll be able to find the minimum of this. I think you at least got some idea. I don't expect you to get the whole thing, because here is where I'll stop the discussion on linear algebra, and I wanted to make it difficult for to look difficult, because I want to introduce now calculus for you guys. So there I'll just, you have to revise these lectures in order to make these things sense now. So I'm connecting the algebra to the calculus. Okay, so now we'll learn about this differentiation, integration, stuff like that, and I'll leave this algebra over here, and in the next session we'll be covering PCA, and then we'll be covering singular value decomposition and the matrix, other matrix factorizations. So these will be primary topics. Then matrix factorization, in that we'll be covering uh, LU decomposition. We have covered everything. We just need to put the pieces together. LU decomposition, I'll again go through what's called as QR decomposition, and you have seen that this S lambda S inverse decomposition, which we call a diagonalization, and there are other decomposition as well, which we'll call as positive matrix factorization, and there is something called as binary matrix factorization, BMF. This is an NP hard problem though, but I'll try to cover most of these. This will be the plan, and then we'll start with the calculus.